Hello and welcome to this lecture. So, we are going to quickly see this notion of an orthogonal complement or dual in this lecture. Okay, so, this is a very important idea. Again, all these ideas are based on the inner product, and these things will help us towards understanding and solving problems like linear fit and all that. Okay, so, it is important to know what this is. Okay. The orthogonal complement of a vector u denoted, notice this notation, I put this sort of curvy braces v and then I put a perp there. Okay, so, this is the notation. What is the definition? It is defined as the set of all vectors that are orthogonal to v. Okay, so, here is a notation. Let us unpack this notation here. This v perp is set of all u such that u dot v is 0. Okay, all the u such that u dot v is 0 makes up this v perp. Okay, so, here is a picture for you. So, I have my x axis, y axis, I have my vector u. What is v perp? It is this line, right? So, everything that is perpendicular to this guy, this line is perpendicular, this is 90 degrees, okay, I have not shown that here, this is 90 degrees. So, this entire line is my v perp, right? Any vector on this line is going to be perpendicular to v. Is that okay? I hope you see that. Now, notice this other curious fact. If u dot v is 0, then u dot cv is also 0 for all scalar c. So, this red line, while we started it out as saying it is perpendicular to v, it is actually perpendicular to the entire line that connects v and the origin. Okay, this entire white line is actually perpendicular to this red line. Okay, so this v perp, right, one vector perp is actually the line through the origin and v perp. The entire line, if you say I want all the vectors that are orthogonal to all the vectors on this line, then you get the red line. Okay, so this leads us to the definition of orthogonal complement or dual of a subspace. Yes, so what do we know about this white line passing through the origin? It is a subspace, right? Let us say you have a subspace S, you denote the orthogonal complement or dual by S perp now. Okay, so this is defined as a set of all vectors that are orthogonal to all vectors in S. Okay, so notice how this works here. So this perp, there is a lot of alls going on here. So this perp is a set of all u such that u dot v is 0, not just for a single v, but all v in S. All the v in S, this u has to be perpendicular to, and we know that it is possible, right. So, this is how it works for the straight lines. Okay, so, this dual is sort of important. It gives you what has no component along v, right. So, it is orthogonal to v. Okay. So, let us list out subspaces and their duals in R2. Okay. So, supposing subspaces we know, right, the subspaces in R2 there are only 3 of them, dimension is 0, 1, 2. It could either be the origin, line through origin or entire plane, and the dual is very easy to find out. Supposing the subspace is the origin, then the dual is the entire plane, isn't it? So, it is every vector is orthogonal to the origin. Okay, so, that is easy. Likewise, 2 is also easy. Let us go to the bottommost case. If dimension is 2 and your subspace is the entire plane, then your dual is just the origin, right? If you have the entire plane, you want a vector to be orthogonal to the entire plane, you can only get the origin, nothing else will be orthogonal to the entire plane. Right? Any vector v, if you dot it with itself, if it is non-zero, you dot it with itself, you get something non-zero, right, positive. So, if it has to be perpendicular to all the vectors, it has to be the origin only. Okay. Now, line through origin is the interesting question. Supposing you have a line through the origin, you can take the perpendicular line through the origin, line perpendicular to this line, then you get the dual. Okay. So, here are the properties. The dual S perp is also a subspace. Okay. So, clearly you see in every case here you got a subspace here, and the dimension is 2. The sum of the dimension of the dual and the original subspace is 2. Okay. So, it's sort of like a rank nullity result, but it's not exactly that, but it's like similar to that. Okay. So, if you add the dimension of the subspace and the dimension of the dual, you always get 2. Okay. It's a nice thing to remember. And it has this sort of curious double property. If you take the dual and take a dual of that, then you get S itself. So, you can see here, you start with the origin, you go to the entire plane, dual once again, dual of the entire plane is origin. So, you come back here. You take a line through the origin, you do a dual, it is a perpendicular line. Now, if you take the dual of that perpendicular line, you will get back to the original line. Okay, these are very, very easy to prove in R2. So, you get all these 3 properties. Now, these properties are more special, they are more general than R2, but anyway, for R2 the proof is very, very easy. Okay. So, here are a couple of problems, I just want you to think about them. Span of 1, 2, it's the straight line multiples of 1, 2. Okay. So, a, 2a, and how do you find the dual here? So, you just watch out for that, be very careful. This is, you have to put it like a, so if you do span of 1, 2, this is my S, okay. So if you want, you can picture this. So this is basically set of all A comma 2A in let's say R, we'll just keep it as R just for simplicity, okay. This is all A to A. Now, how do you think of the orthogonal thing here, right? So I need an xy, right? So what will be in SPURP will have xy such that xy dot A to A, which is 0, right, for all A. Okay. Now, what is this dot product? Ax plus 2ay equals 0. So that is the same as A will come out, A times x plus 2y equal to 0. So for all A, if this has to be 0, that implies x plus 2y equals 0. Is that okay? So I hope you see that. So this is quite easy to see. So this gives you the subspace that is there. So if you want to picture this, what is span of 1, 2, A comma 2A? Okay, so it will be this line, a line like this, right? So this is y equals 2x. Okay, this is A comma 2A. Now this is x plus 2y is 0, so that will be perpendicular to this like that. Okay, so this is x plus 2y equals 0, or you can say x equals minus 2y, or y equals minus x by 2. Okay, so it's a different line. Okay, so I hope you see that. This is y equals 2x and this is x plus 2y is 0. So it's easy in these cases. In more general cases, it may become a little bit more complicated, but otherwise it's easy to do. Okay. Now what about x plus y is 0? How do you find the dual of x plus y is 0? So you have to just be a little bit more watchful here. So if you say x plus y is 0, okay, I want the dual of this, okay. So be a little bit more careful, don't just jump to some conclusion here. So this, what is x plus y is 0? So this is the same as y equals minus x, okay. So if you take x as a free variable, y becomes minus x. So this is the set of all, right, A comma minus A such that A in R. Okay. So you go through the same sort of argument here. You're going to get the dual. This is S. The dual is going to be set of all x y such that the dot product is 0. So it's just A times, let me just write it more carefully, x y dot A comma minus A is 0. So if you simplify that, you get A into x minus y equals 0. So this implies x minus y is 0. So once again, you can draw that x plus y equals 0 is this line, okay, this line, and then this is the dual, and this is y equals x. Okay, so let's pay attention to how the subspace is defined and how the dual is defined. The last one is 2x plus 3y is 7. Okay, so first thing you realize it's not a subspace. So how do you deal with things if it's not a subspace? 2x plus 3y is 7. Okay, so remember this is parallel to 2x plus 3y is 0. Okay, so in the dual of this, the dual of 2x plus 3y is 0 will contain everything that is perpendicular to this, because these two are parallel. So it's enough if you work with 2x plus 3y is 0. Okay, so you define S as, so this is the same as y equals minus 2x by 3. So S A comma minus 2a by 3 for all A in R, and SPURP is what you need. Okay, so this is directly computable and you will get the answer. Okay, so this line that doesn't go through the origin is not too difficult. One can easily work with that. Okay, thank you very much.